Hi, everyone. Welcome to this month's Astronomy on Tap. We're coming to you live from Baton Rouge. This month, we have two lovely out-of-town speakers for you guys, and hopefully we'll be able to return to our in-person shows in the fall, so definitely get excited for that. Before we get started, here are the usual ground rules. Number one, be considerate in the chat. We've never had any issues, but it's always worth saying. Number two, feel free to drop any questions that you have for our speakers into the chat at any point during the talk. And after the talk is over, I will field those questions to the speaker for you. Number three, as always, please consider donating to our Venmo and PayPal. We'll have some people put the links in the chat. And as per usual, we like to add some competition to our donations. This month, we're pitting two of this month's bizarre headlines against each other, local to Baton Rouge. The piranha in the LSU lakes and the python found at the Mall of Louisiana. We want to know, which one would you rather take on in a fight? If you do choose to make a donation, we would appreciate it so much if you would write your answer to that in the memo section. And fourth and last, please like this video if you're watching and subscribe to our YouTube channel. Those two things actually help us out so much. So without any further ado, we'll move right on to today's talks. First up, we have a graduate student at the University of Indiana. He's a native Oklahoman and actually my former game master in Dungeons & Dragons, fun fact. You can also catch him live on Twitch this Saturday playing a tabletop RPG. I'm sure you can find the details on his Twitter. And he's here today to tell us about his work with N-body simulations and other important simulation work. So here is Ethan White.
All right, let me see if I can get this going. So thank you, Courtney. As she said, my name is Ethan White. I am a graduate student at Indiana University. I usually work on globular clusters, but today I'm going to tell you how to create, how we go about creating a real fake universe. So let's see. It's kind of, there we go. So generally, when we think about astronomy, we go into sort of two broad categories, being observational and theoretical. We also have instrumentation, which kind of helps build the telescopes, but for today, let's just focus on these two. Now, observational is, your typical, what do you think of astronomy? You think of observatories, giant telescopes, and some of the pictures that you would see. Now, technically, this is from Hubble. This is a space telescope, and what I just showed you is a ground telescope, but this is the general idea of what you think of when you think of astronomy. But there's this other side, which is the theoretical side. Now that might sound sort of complicated, which it sometimes can be, but it might also sound sort of boring. But theoretical work is a lot more than just blackboards and equations. Now, certainly equations play a large part in theory. We talk about equations in order to sort of understand the physical concepts that govern, the universe. But the reason behind using these is sort of to gain a better understanding of what's actually going on and create some testable predictions that we can then compare with observations to see if our guesses, our estimates, our theory is correct or incorrect. And a powerful tool that we use when doing theoretical work is simulations. Now, what I mean by that is sort of creating a fake sort of set of part of physics and running it and seeing what happens. Now, why do we need to do this? Well, it's because things in astronomy happen very slowly. Something is considered fast in astronomy when it happens over about 1,000 or so years. And some of the things that we're interested in can take thousands, millions, even billions of years to happen. And so using these simulations, we can look at something over its entire lifetime in a matter of hours. Now, there are a number of different kinds of simulations. I'll just mention two here to give you sort of an idea. One would be sort of hydrodynamical simulations. Here we have an example, visualization of a hydrodynamical simulation of a population 3, a very old massive star being created. And for example, another example would be in-body simulations. I'll get to what that means in just a minute because we're going to be talking about that in quite a bit of detail today. And over here, an example of an in-body simulation is a cosmological simulation creating the large-scale structure of the entire universe. Now, and these simulations can be done for a number of different situations, whether it's cosmology, stars, planets, whatever you want to learn about. Whatever you want to learn about will determine the kind of simulation you want to do and the tools that you'll use to do it. So, like I said, we're going to be talking a little bit in depth about in-body simulations, so it's probably important that I describe what that actually is. So, an in-body simulation, what the N stands for is just a number of particles. It's a placeholder, sort of like X in an algebra equation, where, for example, if N is equal to 100, then you'll have 100 particles. And those particles could be representative of stars, planets, whatever you want them to be, so long as it can be represented by a single point. And a lot of the times these are used for dynamics simulations, meaning that we're interested in how these things move around and interact with one another. Now, when you're actually setting up an in-body simulation, you have to, of course, choose how many particles you want, and then set the initial conditions. And what I mean by that is just setting the number of particles, how clustered they are, how spread out they are, if there are any outside forces, say like if you were looking at a star cluster that was in a galaxy, maybe there's a force outside of the cluster that won't necessarily be represented by a particle. There's just everything that is not the number of particles. And at that point, you're ready to evolve the system over time. Now, what does that actually mean, though? So, as I said, these things happen over millions, billions of years, depending on what you're looking at. And so it's not exactly like we can model those in real time. So instead, we have to choose a time step. So, like I said, the time step that you choose will sort of depend on what you're trying to learn. And generally, it could be a few hundred or even 1,000 years. And so you'll take the initial snapshot, if you have, say, your initial conditions, and then you'll take another snapshot after, say, 1,000 years, and after that, and you'll end up with a bit of a flipbook. So let's give an example of a picture example to make that make a little bit more sense. So let's say our N is 2. We have 2 stars here. They have initial conditions going, velocities going up and down, represented by the black arrows, and there's the force of gravity between them. So this is our initial conditions. Let's say we evolve the system in time, so we'll jump to a few years in the future, and after that, and we can see this sort of the simulation. Oh, you might be able to hear my dogs in the background. See the simulation evolve over time. But this is a very simple example. Let's move on to something a bit more interesting. So what I'm about to show you is a visualization of a simulation done by Chris Mijos and Lars Hernquist of 2 galaxies colliding. Now, as I said, one of the big parts of simulations is sort of understanding the physics and then comparing those with observations to see whether or not we're on the right track, whether or not we have the right ideas. And so what we see here is this galaxy simulation is evolving, and then we are comparing it with a real observation that we see in the sky. Now, preferably we'd want to watch the system evolve in real time in real life, but like I said, it opens over a long, long time. But the universe is big, and so if we look in a different part of the sky, we might be able to see the same situation happening with different galaxies, but perhaps at different times in the process. And so what we're seeing here is that the simulation is evolving, we're turning to get the line of sight correct, and then comparing with a real observation. And what this is telling us is that, at least in this case, we know enough about the physics going on that we can accurately predict and recreate what we see in the universe. But it wasn't always so accurate. It wasn't always so simple as what it is now. So, as we'll see, let's go ahead and step back a little bit and see sort of where we began with this. So we're going to jump about 80 years into the past and look at a paper called On the Clustering Tendencies Among the Nebulae. This is one of the first astrophysical simulations that I could find, at least definitely the first in-body simulation. And it consists of 2 nebulae, or clusters of stars, each one containing 37 stars. Now, in an in-body simulation, for each time step, you need to say, let's say we've got the star at the top. You need to calculate the force it feels from this star and this star and this star, all other 73 stars in the simulation, and then you need to do that for each of the stars in the simulation. So if you're doing this by hand, it's going to take a long, long time. And on top of that, you have to do this for each time step. And if you remember, this is 80 years ago. So it's far before the digital computers. This experiment was done in 1941, and the first computers were made in about 1945 or 46. So this would be a lot of calculations and isn't really feasible if you want to do this kind of work. But the author of this paper had an ingenious idea. What they did is, instead of using particles like we would in a computer, they used light bulbs. Each star was represented by a light bulb, and the mass of that star was how bright it was. If you're doing these sort of dynamical simulations, a lot of the times you're only worried about gravity. So for that, you just need to know how massive things are and how far apart they are. And by placing these light bulbs of different brightnesses at different points, that's all you need. And then on top of that, they used what's called a photocell and a galvanometer to measure how bright the amount of brightness at a given point, and related that to the force that it felt. So if you had a light shining on it from this angle, but there was a lot of light here, it'd feel the most force in that direction. So this is great. This gets rid of all those calculations that you needed to do for each star on 73 stars, and then that calculation 74 times on top of that. It's a lot of work, now all reduced down to one measurement of how bright things are. So now that they had this, all they had to do was evolve the system. So find the force on a given point just by measuring the intensity of the light with the setup that I showed you before. Then the hard part comes because they had to manually move these light bulbs the amount of distance they had given their time step. And you can imagine that not only are there a lot of these, but you have to be incredibly precise. Yes, incredibly precise. And just have to move it very, very precisely. And then the hard part then comes with, it's not working. There we go. Repeating that step over and over every time step until you get to when you want to end your simulation. And that's how you end up going from this right here, which is essentially the initial conditions, these nebulae moving in these different directions, rotating along the curved arrows, repeating this, finding force, moving the light bulbs, repeating until you get to something like this. And what they found here is that the light bulbs, the stars on the outside of these nebula, sort of began to be pulled away from the center of the cluster and form these arms, which is a really interesting result for 1941, far before you would imagine anything like this would happen. I think this one is really neat. But as you might imagine, this isn't how we do things nowadays. It would be very difficult to do that simulation that we just saw the video of, doing it all by hand. So a more modern in-body simulation, as you might imagine, uses computers. Some examples of programs used to actually make and run these are In-Body 6, which I use, or Gadgets, which is just a few in-body things capable of running these in-body simulations. And they use, as you might also imagine, a lot more particles. So as I said, I work with globular clusters. This is just an example of something that I made for a class project, and it has 10,000 stars. So it already has far more stars than the previous thing that we were working with, and it ran in like 2 hours. And just for clarity in this figure here, each blue dot is a star, and the green line around it is just the what we consider to be the edge of the cluster. But there are a lot of stars, and they run much faster now with a lot less manual labor. And just sort of as a scale thing, I was curious, what is the biggest in-body simulation that's been done so far? And I looked it up, and it was a cosmological simulation with 4.4 trillion particles. So if you thought that 10,000 would be able to do manually, 4.4 trillion would be sort of out of the question. But so you can see that things are much more advanced now. And the amount, just as a point of clarification, the amount of particles that we want to use depends on what we're trying to learn. If you need to have a sort of small scale structure of things, you might want a lot of particles to see how things are working. But so like in a globular cluster, 10,000 is pretty accurate for what you want to do, but it would be far too small for a cosmological simulation where you're looking on the order of 4.4 trillion. Now, I want to go to what I would like to call the future of simulations, but what I'll call a potential future, and maybe even, a potential future, because this focuses on one facet of these simulations, specifically three-body interactions. Now, what does that mean? Well, two particles are trivial. That's the case that I showed you before. The math to figure out where these things will be at any given point in their orbits, it can be done in the back of an envelope. But as soon as you add a third particle, things become a little bit more complex. And this can really slow down the simulation. And if these three particles are close together and interacting, even if you have a 10,000 particle simulation, these three stars can really bog things down for the whole thing. So the answer, or at least an answer that has been thought of so far, is neural networks, or otherwise known as machine learning. And when we're talking about this, we're going to be talking about one of my favorite paper titles, which definitely has my favorite figure that I've seen in a paper: Newton versus the Machine, Solving the Chaotic Three-Body Problem Using Deep Neural Networks. And for some reason, they felt it necessary to include a picture of Sir Isaac Newton staring at the basic idea of a neural network, which I found funny. So what is a neural network? What does it mean? How can we use it to improve the speed of our in-body simulations? So as I said, it's a type of machine learning in which in this case, you would input some simulations which you already know the outcome to. And that would teach the network what these simulations are supposed to look like, what you should expect when doing them. With the result being that you could input a new simulation that you don't have the outcome for, and that the neural network will estimate the outcome. And so let's look at this figure that we have here on the right side. Each of these dots represent the initial positions of three particles, of three stars in this case. And the solid lines are the orbits of these stars estimated by the neural network, and the dashed lines are the orbits of these stars as actually done by the in-body simulation. Now you might be thinking, I don't really see any dashed lines, and that's because the neural network matches them so closely, at least in these examples. Now, the purpose of this would be to take it to where you're about to get in your big simulation. If you're about to have a three-body encounter, you stop it, you take these stars, put them into the neural network, have the neural network solve it, and then put it back into the simulation when that interaction is done, and once it would have stopped slowing down the simulation. Now, you might be thinking, well, that seems sort of complicated. Why would you take it out? Why wouldn't you just let it run? And that's because using the neural network, they found, was 100 million times faster than the in-body simulation. So, as you can see, this is pretty significant, but this is for a specific type of simulation, or a specific aspect of the in-body simulation. And what this allows us to do is, run more simulations, which can help us get more accurate simulations, learn more about science, and more about what's going on here. Now, I've kind of gotten into the weeds. I want to bring us back to sort of what we were talking about as a whole as we come to a close here. And that's simulations are a very powerful tool. And sort of the goal of which is to learn about the universe and be able to compare it with what we see to either confirm or deny and move forward with what we think about science, what we think is going on. And an aspect of that is that they can sort of be used as a time machine. As we saw in that video that I showed beginning, we see that we can evolve the simulation and then match with something that we actually see in the universe today. And that means that we can have some confidence that, okay, well, we know what it looks like now, and we know that we got there correctly. Well, what does it look like in the future? But it can also mean that if we know that we got to that point correctly, we can think about what it looked like in the past because we have those snapshots leading up to what we see today. It can also help us to explain the unseen. If you run many different simulations with many different initial conditions, you can see what ends up looking the most like what we see in the sky. So, for example, like dark matter, we can't observe it directly, but we can see the results of it. So we can test a whole bunch of different dark matter models using those different initial conditions, run all these different simulations and see, well, which one looks most like what we actually see in our observations. And then finally, there's some error and uncertainty. And so in simulations, so you want to run multiple simulations to make sure that, well, our first result matched. Let's make sure it wasn't a fluke. Run it again, reduce the error, make it more accurate, which can take us from a fake universe to a more reliable, more accurate, real fake universe. So thank you.
All right. Great talk. If you want to unshare your screen, we can start the Q&A. So while we're doing that, there's a bit of a delay. So if you are in the chat, just type your question right in the chat and I'll field it. But as per usual, the most important part of the show is the speakers. So we have to get to know the speakers, right? So I have a couple of questions for you about you and not about your science. First up, what would you say a normal day of work looks like for you?
That depends. So I just finished up my qualifying exams. So now I've just started like really getting into the work. And so a lot of that is, it could be a very, busy day with meetings and code writing, or it could be pretty laid back where, okay, I've written my code, I've done the simulations, I'm going to set all that analysis of analyzing all 600 of these snapshots and just sort of like work on something else, read some papers and things like that.
Okay. Sorry, a bit of an echo. But anyways, totally lost my train of thought. My next question for you is, what would you say is your favorite part of being an astronomer?
I sort of being able to sort of contribute to science in a way that I know can't be misused or anything like that is a large part of why I like astronomy. Is the work I do is fun and interesting, but it's not gonna, no one can misappropriate or anything like that. But also, I like working with computers. I enjoy coding, even though I'm not that great at it.
None of them.
No, that's our secret. But yeah, there's also just a lot of, I have yet to meet anyone in astronomy who's like terrible. Everyone seems very, very nice.
That's always a good thing.
Yeah.
The next thing, what are your hobbies like outside of science? Obviously I know, but for our viewers, like, yes, what do you do outside of work?
I like to play some video games, although that's sort of waned off as I've been busy with classes and things like that. As you know, and as you said before, I enjoy playing Dungeons and Dragons. We have an online game that I'm part of, and then a game that I'm running for some of the other graduate students at IU. Also playing Magic the Gathering. One of my other friends came up from Texas because I was going to be in town. I'm in Oklahoma right now, and so we've been doing that a lot recently.
That's fun. And then the last question about you, in honor of Tabby's son Jude. Every month we like to ask, what is your favorite Pokemon?
So that's a big question. I like myself a Totodile. I've got my props here. I like myself a Gengar. He's always good. But I'm very basic. My favorite is just the Pikachu.
Alrighty. Well, that's the one we normally tell people who know nothing about Pokemon to say.
Yeah.
So
it's a safe answer.
Yeah. Okay. And then on to the science question. So as per usual, I also get the honor of asking the first science question. I wanted to ask you, have you seen those visualizations of what the sky would look like as Andromeda and the Milky Way collide?
Maybe not in a while though.
I can pull them up. I know I'm kind of throwing Alex here for a loop, but I'm actually going to pull them up just because I have them open and I thought it would be nice to show everyone these.
Yeah.
So I just pulled up a tweet with these. And basically, this is a set of visualizations showing what the sky would look like if we were to collide with Andromeda and what that would look like over time. And they're really cool and interesting, especially as you start to get into like the later phases of the merger and you get all this weird, crazy stuff going on in the sky. And I just wanted to ask, how like realistic do you think this is as someone who looks at simulations a lot?
Well, it's just sort of through a loop because that's not quite my area. But as things shouldn't be too disrupted by Andromeda actually colliding. Even though I think the sun will be very big by that point, so we'll have other problems. But it seems fine as far as I can tell.
All righty. And then the first question that we have from the chat is from Mars, and they're asking, how long does it take for you to run a simulation? Or probably just any simulation in general?
Sure. So that can very much depend. Like I was saying, that 10,000 one that I just did for class took a few hours, not too awful long. The ones that I'm working with right now, the simulations that I'm working with right now, were actually done by a former postdoc of my advisor, and so I don't actually know how long those took to run. But it's depending on the number of particles, it can take from a few hours to a few days. And I think there was a review paper that I was reading called like the million body problem or something like that, and it was a million particles. So that took a while.
Yeah. Okay, and then an extension question from Cassidy. She asks, what do you do while your simulation is running to check on it and make sure it isn't doing anything wild?
So, at least with globular clusters, which for anyone who doesn't know is a old star cluster, it should be working fine, or else it'll give you an error. And that'll happen. Or like actually sort of relevant to what I was talking about at the end there, these sort of close encounters. If the stars get too close together, it's not like they won't collide very often, at least not in a globular cluster. But it will slow things down, and sort of you have to tell the simulation, it's okay, keep going. But yeah, for the most part, they should just work unless it tells you otherwise. Okay, well,
that actually tells you that it's not working, because I've worked with many a code that just don't work and they don't tell you about it. Our next question about science from the Flick is, how do people prove and come up with the calculations necessary to figure all of this out? The scale is very hard to understand.
It can be difficult. That is the part of theory that I didn't really talk about today, and that is the equations and the just sort of reading papers, understanding everything, and then making sure it all works together. And that's far beyond what I do currently, at least. But that is, I'm very thankful to the people who have done that already.
Another question from the Zeus this time is, how accurate are the data sets that these simulations use, or is it an estimation? I assume maybe they mean the neural nets and like the training sets or something like that.
So in general, we're working from, sort of in a general simulation where we set up the rules that it'll follow, sort of like, this is how gravity works. This is if we have an external field, like from the galaxy acting on it. That's set up by theory and things that people have either seen observationally or figured out from previous simulations. But in the neural net case, they just have to feed it a lot of a lot of examples for it to learn how to work. And I would say that if you were to use this on your own simulations, the neural net that is, you would probably have to train it pretty extensively so that it knows what your set of conditions looks like to be accurate.
Okay. And then the last science question is going to be from me. And I just want to know, like, what are you working on? Like, what specific thing are you trying to model right now?
So we are currently working, like I said, with a in-body simulation of a globular cluster, which has two populations of stars in it. And we want to see how those populations look over time. So a population of stars, which just means this one is older than this one. And right now we're trying to do some kernel density estimates and look for the eccentricity of those densities at different positions. And currently it's given us some difficulties because it isn't looking how we expect it to look, but maybe that's just something new. But
Alrighty, very cool. So we are going to take a break for intermission now. Before we do, I would like to humbly ask you yet again to consider donating to our Venmo or PayPal, and all of that information will be on our slides in the intermission. And if you do, in the comments, let us know, would you rather take on in a fight the piranha that they found at the LSE Lakes or the python that they found in the Mall of Louisiana? So just let us know. And we will take a quick break and we will be back at 7:37, which is a very random time, but we'll see you then. everyone, and welcome back to the second half of Astronomy on Tap in Baton Rouge. I'm going to skip all of the introductory stuff and move straight on into introducing our second speaker for you guys. So next up, we have a graduate student who's at UC Davis and also works with simulations, but instead, they're going to tell us today about the physics of Star Trek. And in addition to being a general sci-fi fan, he also enjoys biking and writes for Astrobytes. So you should check out his articles on Astrobytes if you want to. And I'm very happy to introduce our second speaker today, Pratik Gandhi.
Hey everybody, big thanks to all the organizers here for having me today. And now that Ethan's told you all about his globular cluster simulations and how those work, I thought, we'll switch gears a little and talk maybe a little sci-fi. I'll share my screen now and hope that it works on the first try. Is this visible for everyone?
It's visible. You got the box thing going.
Yeah, so I'll just hide that in a sec. All right, awesome. So cool. So like Courtney mentioned, I really, really enjoy watching Star Trek. It's really my go-to thing to watch on most days. And
I'm sorry, I don't mean to interrupt you. You still have
you still have the box. Okay. Is that better?
Yeah, that's fine.
Perfect. Thank you. Sorry about that. But I guess what I was going to say was, even if you're not a fan of Star Trek or you haven't seen it before, hopefully you'll enjoy this talk. And I'm going to try and step through a lot of the cool sci-fi that they have in the show, and then where we currently are at with science and technology and how close we are at to replicating some of that. So a super lightning quick timeline of the show and the movies itself for those of you that haven't really watched Star Trek. So it all began in the 60s with what's called the original series. It was, at the time, it was groundbreaking. When you watch it now, it's super cheesy, it's super campy, but you still love it. This, through the 80s and 90s, led to 4 other TV series: The Next Generation, Deep Space Nine, Voyager, and Enterprise. And together they were a lot more popular than the original series, but they all kind of built on that foundation. There have also been about 13 motion pictures in the Star Trek franchise. And then most recently, there have been 3 or 4 new series that have come out in the 2010s and 2020s. So the franchise is still going very strong. And in universe, when you talk about the timeline within the shows and the movies itself, they span the years from 2063 to about 2378. So from not that far in the future to the 24th century. So it's super interesting to see what they imagined those years would look like and where we are at right now compared to those. And they're best known for some of the sci-fi and the tech that they've imagined in the show. And we'll see how in some ways we've kind of come close to replicating some of their technology, but in a lot of other ways we're nowhere near. And we've barely begun to scratch the surface of what's possible and what's not possible. So at its core, Star Trek really is about exploring the galaxy and exploring the universe and, meeting alien civilizations and interacting with them. And really the linchpin for all of this exploration is what they call warp drive. And warp drive is the technology that allows for faster than light travel in the show. And it's really what made possible all of their traveling, their galactic civilization, trade, exploration, etc. I'll just play a clip here from The Next Generation.
Set a course for the Viridian system, maximum warp.
So it's almost always like that. The captain usually says something like warp factor 6, engage. And then, the music kind of swells and the ship jumps into warp. And everyone's like, yeah. And it's super cool. But, how realistic is it? And in terms of our theories and our understanding of physics, is it even remotely possible to reproduce something like this? And just to sort of give you a frame of reference, When you talk about warp factor 1, that's traveling at the speed of light. Warp factor 10, which is the maximum level on that scale, is basically traveling at infinite speed. And even in the Star Trek universe with all of their sci-fi, that's kind of impossible. So like 9.99 would be the highest warp speed that you can achieve. So as we reflect on warp drive, I guess a good thing to think about is what's the furthest we've ever sent something into space or sent a spacecraft out? And the answer to that, of course, is the Voyager probes, which recently, and by recently I mean a few years ago, crossed over the outer boundaries of our solar system. They were launched all the way back in the 70s, right? And it took them like 40 to 50 years to even just get outside of the solar system. And they're nowhere close to even approaching the nearest star to us, Proxima Centauri. And that's just to give you an idea of just how difficult it is to achieve interstellar travel, let alone explore, the entire galaxy like they do in Star Trek. And so I guess the question is, how close are we to achieving even step one of that, which would be traveling to the nearest stars? And of course, we have rocket technology, and that's improved a fair bit since the 70s, but relative to, warp drive and other stuff in Star Trek, rockets are really, really quite slow. So let's look at some alternative technologies that people are thinking about and theorizing that might help us get closer to achieving interstellar travel. The first one is an idea called a solar sail. And that's essentially it's, I guess, analogous to having a sailboat, but in space, where the sail is made up of really reflective material. So the idea would be that the radiation from the sun would create a pressure on the sail that's strong enough to really accelerate the ship to really high velocities. And a drawback of this, would be to, of course, find a material that would be good enough for this, build a large enough sail to be able to harness the sun's power. And even with all of that, it would still take a while for the ship to be able to accelerate up to light speeds or even just very high speeds. So another alternative that people think about are what are called fusion engines, which is essentially the same idea as a rocket, where you sort of propel material out one end to make it go in the other direction. But in this case, instead of burning fuel, the idea would be to use hydrogen fusion, which releases much, much larger amounts of energy and would hopefully provide much higher accelerations to the rocket than conventional fuels. And as you can probably imagine, the biggest drawback of this would be that it's incredibly hard to achieve sustained hydrogen fusion. We haven't been able to do that except in hydrogen bombs, and even then for a short period of time. And B, it's potentially also very, very dangerous if something were to go wrong. So, these are sort of two of the leading ideas that are out there for achieving travel that's closer to light speeds. But really, when you think about it, if we are trying to consider how close we are to achieving warp drive as they have in Star Trek, where are we at in terms of that? So thinking about technologies that may mirror warp drive in real life, in the 90s or the late 90s, there was a physicist from Mexico called Miguel Alcubierre who proposed the idea of something called the Alcubierre warp drive. And the idea that he proposed was that if you could somehow harness enough energy to contract space in front of the ship and expand the space behind the ship, then you've essentially moved the ship forward without actually making the ship accelerate to really high speeds. And one of the other key ideas behind this, hypothesis is that the ship itself would live in a bubble of space that's undisturbed, that's normal, that's neither contracted nor expanded. And one of the limitations that he was trying to work with was that, as per the theory of relativity, which, as far as we know, holds true always, it's impossible to travel faster than the speed of light. But that does not hold true for space and time itself. So if you're able to contract and stretch space-time faster than the speed of light without actually having the ship move faster than the speed of light, that could be one potential workaround to this problem of not being able to go faster than light. And so this was like this idea that was put forward by him and a few other people. And since then, a lot of people have been trying to figure out if this is even like a remotely valid idea and if this is ever going to be possible. And there are a lot of small scale experiments going on, like this one at the NASA Johnson Space Center, where they're trying to create like a tabletop warp drive, essentially just a really, really small warp bubble to try and test if this is even possible. And the problem with this is that it takes an incredible amount of energy to even consider doing this on a very small scale. So doing this on a scale that's as large as a starship is almost unimaginable right now. So as of today, as of 2021, we're just so far away from this kind of technology that it's really within the realm of sci-fi and not within the realm of science right now. And we don't even have full consensus among scientists whether this is possible or not. So, that's like an overview of what warp drive could be like. But as another reminder, or as another interesting thing to note, even at the maximum possible warp that's achievable in Star Trek, this warp 9.9, the nearest star, Proxima Centauri, would still be 18 hours away and traveling at maximum warp. And that, again, just goes to show, astronomers really love talking about how big space is and how empty space is. But I think that really just drives home the idea that there really is unimaginable amounts of space, even between us and the nearest star system. So now that we've looked a lot at warp drive, I want to move on to some of the other sci-fi ideas in Star Trek. The next one is much more relatable. It's the idea of using touchscreens. This is something that was not in the original series. They still had like analog controls and buttons and stuff. But starting with the Next Generation and all subsequent shows and movies, their ship was just covered in touchscreens. It basically controlled everything and all of the functions in their ships. So, touchscreens are something that are actually quite common, right, in 2021. And it's a technology that we have come pretty close to perfecting, just like in Star Trek. But one thing that's really cool that I actually didn't know until I was looking up stuff for this talk is that the first prototype touchscreen was developed in the 1960s. And that's something that was completely new to me, and I thought that was pretty cool, given that we think of touchscreens as being like a 21st century invention. But of course, they didn't become fully mainstream and commercial until the late 90s. But given how advanced our touchscreens are in 2021, they still pale in comparison to this one feature that all Star Trek touchscreens seem to have. And that's the idea that in the show, they do stuff like this where they just sit on the touch panels, or they'll be like casually doing stuff near the touch panels. And they never, ever seem to have something even as remotely simple as a butt dial, right? And I feel like that's something that our touchscreens have really not been designed to do yet, is to recognize the difference between intentional and non-intentional touching. But yeah, like every time I watch Star Trek, I worry about them just like sitting on the touchscreens, leaning on them, and it's a whole other question. So moving on to the next bit of sci-fi or technology is the idea of the transporter. And the transporter is really one of my favorite pieces of Star Trek tech. And it's this idea that people use this device to instantly teleport from one location to the other. And it was very, very often used as a plot device in the shows and the movies. So in universe and Star Trek, the way it worked was that things or people were actually disassembled atom by atom, electron by electron, molecule by molecule, and then reassembled at a completely different location. Of course, this is, something that we can't even really consider doing in real life right now. But I wanted to talk a little bit about where we are in terms of teleportation technology and whether that's even possible. So in in recent years, especially like this example from 2017, people have started experimenting with what's called quantum teleportation. This was a team in China that managed to teleport a photon or a light particle from all the way from the surface of the Earth to an orbiting satellite. And I think it's worth unpacking a little bit what quantum teleportation means, because it may not be quite what you think. So there's this phenomenon called quantum entanglement, where there could be two particles. It's possible to create a pair of particles in different locations that have essentially the same properties, such that if you change the properties of one of the particles, the other particle would also change that corresponding property almost instantaneously. And that's the principle that this team used, where they actually had two photons that were part like a quantum entangled pair, one on the surface of the Earth, one on the satellite. And then by changing the properties of the one on the surface of the Earth, they were able to send a signal as if they had teleported that photon all the way up to the satellite. Now, you may think, that's really cool, but that's not real teleportation. And I agree with that. It's just that this is the closest where we've come to, as far as our understanding of physics and our development of technology is concerned, to even remotely achieving any kind of teleportation. But even apart from that, this kind of tech and this idea has a lot of different applications, even outside the realm of teleportation, in quantum computing, in different kinds of information systems, and in trying to develop what's called the quantum internet. So even though this may not be quite like the Star Trek transporter, I think it's still a really cool technology and it's still a really cool idea. So that's warp drive, that's touchscreens, that's transporters. The next piece of technology, and this, if you've watched Star Trek, you can probably guess what I'm getting at, is phasers. And the idea behind phasers is that they were these weapons that they used in Star Trek to, although they mostly spent their time exploring the galaxy, occasionally they had to fight off, the antagonists, whichever alien race happened to be the antagonist in that episode. And for that, they primarily relied on this technology called phaser technology. And they were essentially these just massively powerful ray guns that they could use for a variety of purposes. In this particular image, you see the USS Enterprise firing its, enormous phasers, but they also had smaller handheld versions. And you see Michael Burnham from Star Trek Discovery trying to fire a handheld phaser, which basically looks like a small ray gun in this picture. So in universe and Star Trek, they apparently rely on some kind of technology called nadion particles. And these are completely fictitious. As far as we know, nadions don't exist. So do we have something that's analogous to phasers in real life? And the question is, yeah, we have lasers, right? And lasers are something that most people are pretty familiar with. You have your handheld laser pointers. Even in astronomy, sometimes large telescopes like the Keck Observatory shown here are equipped with lasers to try and refine the resolution of their observations. And both the handheld lasers and the ones used here in astronomy are not really that powerful at all, especially when you compare it to phasers. You can also think about something like a laser cutter, which starts to get slightly closer towards the realm of phaser technology, which if you've ever worked in a machine shop, you'd know that you use lasers to basically like cut and etch different things. And those are slightly more powerful. If you were to think about a different sci-fi franchise and think about Star Wars, the lightsabers that they used in Star Wars could be thought of as a different kind of laser or phaser technology. And then ultimately, the most powerful laser that we have on Earth is actually one that's being used to try and develop hydrogen fusion technology for generating clean power. But even this most powerful laser that we currently have on Earth doesn't yet come close to matching the raw power that phasers had in Star Trek. And this next screen is just to give you an idea of the scales of power used in these various technologies, where a watt is just a unit of power, right? And so you can see that going from all the way from a handheld laser pointer to the phasers on the USS Enterprise, it's really like so many different orders of magnitude apart in power. And although we've created some really powerful lasers on Earth, you see that, that kind of comes close to achieving the power that they have in Star Trek. They're nowhere near as versatile as they are in Star Trek. And this, I think, is where phasers are going to remain in the realm of sci-fi rather than in the realm of science. And by their versatility, what I mean is that on the show, they're just used for a ton of different applications. Like you'll see in this video, sometimes they're just used to randomly stun people and knock them out. Whereas other times they're just able to like explode and destroy things. Sometimes they also use them to like heat objects up to provide a source of light, a source of heat. And then occasionally they'll show them firing phasers and people just kind of instantly disintegrate, or objects just instantly vaporize. And so all of these clips, by the way, were from the original series, and you'll see just how like cheesy and campy some of them are. But the idea that I want to drive home is that, even if we come close to producing lasers that are kind of like phasers in terms of their ability to like cut through things or burn things, I really don't think they're going to be anywhere near as versatile as a single phaser can be in the world of Star Trek. And then finally, after talking about phasers, I want to move on to the last bit of Star Trek technology that I'm going to focus on today. And that's the idea of the cloaking device. This is another very commonly used plot device in Star Trek, where they use these devices to turn anything invisible, usually applied to ships, starships, and they use them to sort of sneak past other ships and basically to render themselves invisible to detection. And in this clip, you're going to see our protagonists on the Enterprise are suddenly surprised by two Romulan starships that were cloaked and then suddenly uncloaked to try and ambush them.
Two Romulan warships uncloaking.
Right. And so, again, the idea that I want to think about today is, are we even remotely close to achieving this kind of invisibility device or cloaking device, right? And there are some ideas out there, and there are some experiments that are being carried out. One idea is to use a certain class of exotic materials that have the property where, just like other materials, they can refract or bend light as the light passes through them, but they actually refract light in the opposite direction than ordinary materials would. And so if you were to surround something in one of these exotic materials that are often called meta materials, then the light would just be bent in a different direction by the meta material and not pass through the object encased within it at all. And that theoretically would render the object encased within the material completely invisible. The problem is that these kinds of exotic materials are really hard to manufacture, also really expensive. They have been proven to work in certain cases, but only in very extreme lab conditions. And most of the times they only work for light of a single frequency or a single color. And so to apply them to just all kinds of visible light is still something that's not been done in the lab. But another option for developing a cloaking device is something that researchers such as this group at the University of Rochester have been working on, where instead of trying to use different kinds of materials, they just set up optical paths or paths of light that are arranged in a clever manner, such that at different points in the path, if you were to place an object and look at it from one end of the path, it would appear as if the object is not there. And that's just because of how they've cleverly arranged so that the light goes around the object at that particular point in the path. And a demonstration of that is, in this image where someone's put their face in the path of the light but it still appears as if that part of their face is just not there. And so these are just, a couple of different ideas of what's possible when it comes to trying to develop a cloaking device. But as you can see, they're still pretty clunky and, nowhere near what they show in Star Trek in terms of cloaking devices. And they're not portable, right? Like this kind of setup would remain in the lab. And so this is kind of like my laundry list of things that I've gone through today, right? All the way from touchscreens to warp drives. And you'll see that in some of these cases, especially like touchscreens or maybe even lasers, we've come pretty close to matching the kind of stuff that they thought would exist in the 24th century. But as far as some of these other things go, like especially like transporters or warp drives, they're still far, far in the realm of science fiction, and we're not even close to trying to even consider how they might be feasible. And so with that, I'd like to end my talk today. Thank you so much for giving me the opportunity to talk here today. Like Courtney mentioned, I am actually one of the organizers here as well, right, for a blog called Astrobytes, and we publish general summaries of astronomy papers for anyone to access and read. So if you're interested in just learning some new astronomy, feel free to check it out. And with that, I'll end my talk. Thank you.
Alrighty, great talk. If you'll unshare your screen, there we go. Perfect. Let me get myself up here. Yes, great talk. And as I did with Ethan, I'm going to start with some questions about you. And I'll give everyone an opportunity to ask their questions in the chat. First thing I wanted to ask you, so a lot of people, when they experience something as a child, especially like scientists, if they experience something, usually sci-fi in their childhood, they tend to carry that with them through their career. Would you say that like Star Trek and sci-fi got you into astronomy, or was it something else?
I'll be completely honest, and I'll say that a large part of the reason I got into science was my parents just being like, oh, you should study science. And then, I did a lot of it in school and realized that I was fairly decent at it. But yeah, Star Trek was definitely something that I really enjoyed as a kid. And I'm sure it played at least some part in getting me excited about astronomy. Because at the time, it's not like my parents said, oh, you should study astronomy. But it was just more science in general. But yeah, as far as my interest in space and astrophysics is concerned, who knows, maybe a part of it is because of sci-fi.
Okay. What to you still attracts you to sci-fi as a scientist? I know a lot of times scientists will be like, sci-fi is a little too like weird and like not real science. So what keeps you coming back and what attracts you to it?
Yeah, so I guess I'll answer about Star Trek in particular, but I think this applies to a lot of other sci-fi as well, is that, in the end, despite all this talk of warp drives and transporters and cloaking devices, Star Trek really ends up being a show about humanity and the human condition. And very often, most of these like crazy technologies or like all these kinds of inventions are just used as plot devices, right? And then the real narrative arc or the story is really about exploring space and making contact with new people, and then using that to turn a mirror on society itself and trying to address the questions of how we interact with each other, and questions surrounding like race and differences in humans themselves and stuff like that. So I think in the end, as a kid, although I was attracted most to the sci-fi part of Star Trek, as an adult, that's the reason that I keep going back to it. And that's the reason I can rewatch these episodes like 100 times.
Good. And do you think it's important for sci-fi to be realistic, or do you not think it's that important, really?
I think I'm pretty agnostic on that. I tend to enjoy both kinds. I think as long as it has a good story, I don't really care if it's that realistic or not.
And then also, do you have hobbies? I know I had mentioned that you like to bike. Do you have other hobbies outside of science?
Yeah, I guess something that I've recently gotten a lot more into is cooking. And, maybe a lot of us have, given that we're spending more time at home. But yeah, I'd say apart from like science and watching stuff and cooking, I've been spending a lot of my time trying to cook new things and bake.
Fun. Yeah. I think, definitely a lot of people have done that.
Yeah.
And then last question about you. What is your favorite Pokemon?
Right. So I think just like Ethan, I'm going to be pretty mainstream about this and say Squirtle. And usually when I play the Pokemon games, no matter which one, I always start with the water type. So yeah.
Good. I also love Squirtle. Okay. So I'll move on to some science questions. I know that your talk itself was like not necessarily about science in general, so I kind of did a little bit of that. But I wanted to ask you what you thought about like what inspires what. Do you think sci-fi inspires tech, or do you think tech inspires sci-fi, especially when it comes to like newer technologies?
Yeah. So I mean, I think it's definitely true that science or tech inspires sci-fi, right? Because even when stuff like Star Trek or anything else was created, in the end, when they talk about exploring the galaxy, they still rely on a lot of the things that astronomers have discovered. Like they talk about nebulae and star formation and supernovae and other things. But I think a bit of it goes the other way too. Like it's definitely true that there were certain manufacturers of cell phones in the 1990s that tried to base their design on like the communicators that they use in Star Trek. And that's part of the reason that they came up with like the standard flip phone design in the first place. I'm not sure if the same was true for like touchscreen devices or not, but yeah, I think it definitely does go the other way too. And if I remember correctly, I think when the first space shuttle was developed, the reason the prototype was named the Enterprise was because Star Trek fans wrote like a massive letter campaign to the people at NASA, and they ended up acquiescing to that.
Yeah, if we did that today, it would be like Bodie McBoatface.
Yeah, exactly.
Okay, so from the chat, first question is from Cassidy Wagner, and she asks, of all the cool Star Trek technology, what would you be most excited to see in real life?
Yeah, I definitely have to say like either the transporters or the cloaking devices. They're just cool. Yeah.
Good. The next question is from Tabby Boyajian, and she says, thanks for the talk. I just watched Star Trek for the first time last weekend. Can you comment on the red matter?
Yeah, so if I remember correctly, that's from the rebooted movie series in 2009. And that's actually one of the things that I haven't thought about a lot because I don't really watch those movies as much. Like I prefer watching The Next Generation and Deep Space Nine a lot of the times. But yeah, it's definitely like a really interesting technology that they came up with just for that movie, because I don't think it's been mentioned in any other parts of Star Trek as far as I know, but I could be wrong.
Okay.
Yeah, sorry if that didn't really answer the question.
Okay.
Yeah.
The next question is from Zeus, and they ask, what does the recent confirmation of gravitational waves at LIGO say about the possibility of warp space travel?
Yeah, so I mean, we definitely know, thanks to stuff like LIGO, that space-time can be warped and that you can have like ripples and waves through space-time. I'm actually not sure if anyone's thought about how that could be applied to something like warp drive, but yeah, definitely an interesting question. I think the real question there would be, how would it be possible to do that manually, and how would it be possible to control the warping of space-time? Because with LIGO or with like black holes or something, it's all just natural phenomena that we can observe them, we can detect them, but we're not really able to control or harness them. But yeah, maybe you could imagine like a ship that kind of rides on waves of space-time.
Like a sailboat.
Yeah, exactly.
And I think I missed one a bit earlier from Mars, and they ask, Are there any current updates on the White Jude warp field experiment?
Yeah, that's an excellent question. I'm not entirely sure. The last I read about it was that it's something that they're still testing. And again, like I mentioned, the problem is, of course, apart from like thinking through the technology, is that it takes a lot of power to try and achieve something like that. And as far as I know, I don't think they've had like a resounding success, but don't quote me on that.
Okay. And then a question not about your talk that I wanted to ask is, I know you're working on simulations. What specifically are you working on?
Yeah, so Ethan mentioned that he was working on globular clusters, right? And so I'm looking at simulations of what are called dwarf galaxies. And those are essentially just smaller galaxies that orbit larger, more massive galaxies. And so I'm focusing on dwarf galaxies of the Milky Way, so satellite galaxies orbiting the Milky Way. And the idea being that we think that those dwarf galaxies were among the first ever galaxies that formed in the universe. And so it's kind of like trying to use them as fossils to understand conditions in the very early universe.
Interesting.
But through simulations.
That's like the small and large Magellanic Clouds, right?
Exactly. And others. There's like a few hundred at this point.
Okay.
That we know. Yeah.
I remember hearing a talk once about one of our dwarf galaxies, our dwarf satellite galaxies, having like a stream of stars behind it.
Yeah. So
explain more about that.
Yeah. So Ethan kind of alluded to this in that simulation he showed of two galaxies merging. But the idea is that when you have two galaxies that come close to each other or start merging, because of the way the gravitational interaction between them works, and because of like the tidal forces between them, it's possible sometimes that usually the less massive galaxy gets kind of distorted in different directions and leads to those like streams of stars and gas that you see, and they're often called tidal tails, I believe.
Cool. Yeah. Alrighty. Well, with that is gonna be everything for the show today. If Ethan wants to come back on, or you guys want to stay on, whatever, it doesn't matter to me. But I wanted to thank both of you very much for giving talks today. We appreciate you so much. We know you guys are busy and that it was kind of last minute, so we're very thankful for you. I also want to shout out our streamers behind the scenes, Allie and Alex. They put all this together, and they do a really awesome job every month. So thank you to them as well. And before we head out, I just want to mention a couple things. If you're watching us asynchronously and not live, do feel free to still interact with us. Subscribe to our channel, like our video. You'll get notifications for our next show. And all of that stuff helps us out quite a bit. And then, as always, keep an eye on our Facebook, Instagram, and Twitter. We post all information about all of our events as soon as we have it. And we hope to see you on YouTube next month. And then sometime in the fall, maybe we'll see you guys all in person again, and hopefully also online at the same time once we figure out how that's going to work. So thank you all very much, and hope you have a great evening.